Hello everyone, and welcome back. Today we are going to discuss Newton's third law, and in order to do so, we're going to start out with a little demo. So here in front of you, you see two little physics carts, red on the left and blue on the right. And if you'll notice, the red cart has two metal bars in it. So other than the color and those two metal bars, these two carts are identical. And the wheels are made so they're almost frictionless, as frictionless as they could be anyway. Each cart also has a plunger attached to it that is spring-loaded. So if I hit a button on the cart, that plunger will shoot out of the cart and push whatever is against it. First, we are actually going to put the two plungers together, and I'm going to hit the buttons simultaneously so the carts actually push off of each other. Just watch what happens, then I'm going to ask you a couple of questions. Now, question one, which cart moved? Well, if you watch, they both moved. However, the larger question is, which cart had a higher acceleration? Let's take a look at this again in slow motion. So as you just saw, it is the blue cart that had the higher acceleration in this case. Now let's change the situation a little bit. I'm only going to allow the red cart to push this time. So put the plunger in, put them together, and hit the button, and watch. Which cart moved? Well, again, they both moved. Which cart had the higher acceleration? Let's watch the slow-mo. Again, the blue cart had the higher acceleration. For most people, this will make a lot of sense because it is the red cart that pushed. Okay then, let's change the situation one more time. This time, it is the blue cart that is going to push. Here we go. Which one moved? Well, they both moved. Which one had the higher acceleration? The blue cart had the higher acceleration again, even though it was the one doing the pushing. In fact, all three of these situations gave pretty identical results. First, they both were pushing on each other, then the red car did the pushing, then the blue car did the pushing. The reason why they had similar results is because from the cart's point of view, whoever is doing the pushing does not matter. If the red car pushes on the blue car automatically pushes back on the plunger of the red car. If the blue car pushes on the red car, then the red car automatically pushes back on the plunger of the blue car. This, in a nutshell, is the basis of Newton's third law. You cannot push on something without that something pushing on you back. If you have a race in a swimming pool, the first thing you do is push on the wall. The wall pushes you back, and then you accelerate away from the wall. If a car pushes on the ground pushes back on the car so the car could speed up from a red light. In fact, that is the exact same third law pair used for how you walk. When you walk down the hallway, you push against the floor. The floor pushes you back so you can actually move forward. Based on third law, all forces in the universe occur in pairs. There is no such thing as a single force existing. They always come in pairs, and these pairs exist on two separate objects. So why did the blue cart have the higher acceleration in all three cases? Well, it's based on the idea that I just mentioned. These two forces, I have force, red on blue, and force, blue on red. It does not matter if the red car is doing the pushing, the blue car is doing the pushing, or if they're both doing the pushing. When one exerts a force on the other exerts the exact same amount of force directly back on the object. So if blue pushes red with 10 newtons of force, then red pushes blue with 10 newtons of force. And it does not matter who is doing the pushing. This is why it is a very bad idea to punch a wall. You may be able to exert a lot of force on that wall, but that wall will exert the exact same amount of force back onto your hand. So if the forces are the same, why did the blue car have the higher acceleration every single time? The answer comes back to Newton's second law, which was described as acceleration equals net force over mass. If we look at the objects individually, the net force on them is the same but in opposite directions. Therefore, the object with the higher acceleration is going to be the one with the lower mass. And in all three cases, the forces were the same, and the blue cart had the lower mass. Therefore, it had the higher acceleration. So, Newton's third law can be written like this. If object A exerts a force on object B, then object B exerts a force on object A that is equal in magnitude and opposite in direction. All forces in the universe occur in pairs, and all those pairs obey these rules. So, let's take this one step further and ask a couple questions to see if you understand. Here we have what is probably the simplest of force diagrams that you will deal with in this class. I have a ball sitting on a table and it is not going anywhere. So let's actually create my force diagram. First, put force Earth on ball. Let's say this is 20 newtons. We also will have force table on ball, which could also be said as force ground perpendicular or force normal. Well, if the ball is not going anywhere, then it has zero acceleration, so that means it would also be 20 newtons. My question is, are these third law pairs? They are equal and they are opposite in direction. Are they third law pairs? Well, the answer is no. They are not third law pairs. Third law pairs must exist completely simultaneously, which means if I can remove one force or change one force without changing the other, then these are not third law pairs. Third law pairs must exist at the same time simultaneously. If one disappears, so does the other. A very easy way to point this out is if I took that ball and dropped it off the table, I would still have force Earth. But if nothing else was touching it, there would be no force table, which means these cannot be third law pairs because they would have to exist at the same time. You may then ask, okay, what are the third law pairs to these forces? Well, the third law pair of these forces are actually in the names. This is force table on ball. Therefore, there must be a force ball on table. In other words, the ball is pushing on the table with 20 newtons. Why is that not on my force diagram? It is not my force diagram because the table is not my target. Remember the first question we asked for any physics problem. 1, what is your target? Target's the ball. Therefore, I do a force diagram of the ball. I'm not doing a force diagram of the table. So even though third law pairs exist, you very often are only drawing one of the two pairs because you're only drawing one of the two objects. Okay then, what is the third law pair to force Earth on ball? Let's ask that with a slightly different question. Here is a skydiver. He has just jumped out of a plane. Now I'm going to make a few adjustments here. One of which is I'm going to completely remove any type of air or air friction from this equation. So there is no air here, and he's still falling toward the Earth. Of course, we have force Earth on person. Let's say that is 250 newtons. What is the third law pair to this force? There is nothing else touching him. So I'm ignoring any air, and it's definitely not when he hits the ground because third law force pairs must exist simultaneously. So as he is falling and accelerating toward the ground, there must be a third law pair that matches 250 newtons. Again, the answer is in the name. And that's one of the reasons why we have this nomenclature. If force Earth on person is 250 newtons, that means the person is exerting a third law pair force on the Earth, I'll call it force person on Earth, that is also 250 newtons. So in other words, if you weigh 150 pounds, the Earth is pulling on you with 150 pounds of force. It also means you are pulling on the Earth with 150 pounds of force. This skydiver, is he accelerating toward the Earth? Absolutely. Is the Earth accelerating toward him? The answer is yes, but as stated before, acceleration is F net over mass. These two forces are equal, but the mass of a single person is going to much less than the mass of the Earth. Therefore, it's going to have a much higher acceleration. Does the Earth accelerate? Yes, but the mass is so large compared to the force that acceleration is probably so tiny it's probably not even measurable. So let's do one more problem. I think I may leave this one to you. You are placed in the middle of a magic frozen pond. You are not moving at all, your velocity is 0. The pond is magic because the ice is perfectly flat, you cannot chip the ice, you cannot melt it in any way, and it is perfectly frictionless. You have your winter clothing, your school backpack, and your physics textbook. My question to you is, how do you get off this pond? And to knock a few things out, you cannot walk off no matter how slowly you try, you cannot crawl, you cannot roll, and if you try to jump, the only direction you're going is upward. And we're still ignoring any type of air resistance, so you cannot blow yourself off the ice. How do you get off? Okay, to wrap things up, here are Newton's 3 laws. Newton's first law, an object in an inertial reference frame will maintain a constant velocity if all forces exerted on are balanced, and will change velocity if they are unbalanced. Newton's second law, the acceleration of an object is directly proportional to the net force exerted on it divided by its mass. And Newton's third law, if object A exerts a force on object B, then object B exerts a force on object A that is equal in magnitude and opposite in direction. I hope this lecture has helped you out. Have a good day. This is Mr. M signing off.